Okay, welcome everyone to the last talk of the season. We're really excited to have Shai Levin here, who's a PhD student at the University of Auckland, almost finishing PhD student, who will be talking about isogeny unpredictability assumptions. So take it away.
Thank you, Maria, and thank you guys for having me on the Isogeny Club. It's really cool to give a talk here, writing a PhD now, so it's really nice. I'll just flip all the slides upside down so you guys can see them, because it's not going to be very helpful if they're the right way around. Yeah, so it's a two-part talk. In the first part, I'm going to introduce and motivate an unpredictable function from isogenies. I'll go into a bit more about what that means. And in the second part, I'll talk about how, like in a couple of my papers, which were collaborations, of course, I used generic proof systems to prove isogeny relations. Most of the content from this talk is from a collaboration with Robbie Pedersen, which is on ePrint and is in submission at the moment. But it's also been fleshed out a little bit in my PhD thesis, which I'm going to be submitting soon. Yeah, so feel free to interrupt me with questions as you go. I do like a bit of interaction if something's not clear or if there's any questions. Maybe Maria can help with that. Yeah, so first of all, part one. Somewhat of a philosophical slide here, I guess, to begin with. While I'm not claiming that the conjecture I'm going to propose holds for arbitrary implement CGL hash functions, I just want you to think about this in the back of your mind, is what makes the particular choice of CGL hash function, which I'm going to introduce, amenable to this computational assumption. So, like, what are the things that you can change? Well, you can change how you choose to represent. I mean, first of all, the CGL hash function, I think everyone knows what it is. It's the first cryptographic protocol from Isogenies. How do we actually do it? Well, I mean, there's many different ways. We could choose different representations for our curves. We could use J invariants. We could use a specific model of a curve equation. And then how do we actually define kind of the next step? What particular algebraic expression are we using? And also how we determine direction. So like what is the -1th direction or the 1th direction or the left and right direction? So we kind of have to come up with these, we have to make these choices. What we're not generalizing at the moment is just, well, I'm not generalizing it, but I want you to think about generalizing it. We're not thinking about genus, like higher than 1. And we're not thinking of L not equal to 2. So a lot of, I mean, some of the stuff in this talk will apply to arbitrary L, and some of it won't. But just for simplicity, we're going to focus on the case that L equals 2. And also, we're going to assume that E0 has unknown endomorphism ring, which is a very strong requirement, I know, but it's very hard to actually do things with the CGL hash function without this. And we'll discuss a caveat there where you could potentially avoid it as well. So the CGL hash function, which we introduced in my work with Robbie, was based on radical isogenies. And the benefit of radical isogenies is that the way that you construct the curve equation is backtracking is kind of implicitly, you kind of keep track of kind of the backtracking direction based on the curve equation itself. So like the 0, point is a point of order 2, and that defines essentially the backtracking direction. So we're working over 3 mod 4. That's just something to keep in mind for this talk as well. So we can think about FP squared as FP adjoin J, where J squared is -1. So that's why I'll be referring to, for the rest of this talk, the real and imaginary components of an FP squared element. And that's just to keep the notation nice, and just like how the complex numbers, although it's a finite field. And again, so with the radical isogeny formulas, we can define a step function, and it looks like this. So the next curve in the kind of CGL evaluation at each step, we're going to take bits of the message, and the idea is that we want to kind of fix the square root of C, so that at every curve, there's always going to be one canonical square root. And a very convenient way of doing this for our purpose is to pick the square root that has it has in you'd hope in most cases that the real value is non-zero. And in this scenario, the roots will be minus alpha, the real value of alpha I, and minus the real value of alpha I. And because -1 is a non-quadratic residue, because P is 3 mod 4, it means that exactly always 1 will be a quadratic residue and 1 will be a non-quadratic residue. So we'll just fix the square root to be the one where if the real value is non-zero, the one such that that is a quadratic residue. So in other words, it has a square root. So the square root has a square root. If the real value is 0, then we know that the imaginary value will be non-zero because of the way these curve equations are defined. It's implicit that Ci is non-zero. And because Ci is non-zero, if this is 0, then the imaginary value is non-zero. So we can always fall back on that, and that gives us a deterministic function. Okay. So I fooled you into coming into a protocols talk. Sorry about that. But we're not going to be looking at this algorithm in detail. It's basically just what was in the previous slide. I just wanted to show what the algorithm looks like. The input, it takes E0, so you need a starting curve and the message, of course. And the output will just be the curve equation, the coefficients of the curve equation. And for the remainder of this talk, I might occasionally refer to CGL of M. And what I really mean is I'm starting at E0, which should be implicit in what I'm talking about. And when I say CGL M then K, what I mean is I'm applying CGL starting from E0, evaluating it on M. That's giving me a curve here. And then I'm evaluating the key part. Okay, so I mean, these things should look the same to you. And what I mean by CGL is this specific variant of CGL. Okay. So unpredictable functions. So well, it's a deterministic function, and it will take 2 inputs and give you an output. The first input's kind of like a public parameter, and the second input is really the one you care about. And this is mapping back into the set E. And so what we're really interested in is not the function f itself, but this composition function, where I'm starting by evaluating f with some m, which you could think about as a message. And then in the outer function, I'm then evaluating it on k. And E0 will be some fixed public thing. And we say that f is unpredictable if a polynomial Thom adversary cannot win this game with non-negligible probability. And what happens in this game? It's very simple. You sample a uniformly random key. You publish the walk given by k with the function f. This is kind of like a public key or a commitment to k in some way. The adversary is then given ek and oracle access to this composition function. And it can query it as much as it likes. And then it has to come up with one more input and its corresponding output. It's obviously not allowed to query this to the oracle itself. And so it's kind of just a kind of standard one more assumption. But the key here is that it's much weaker in some sense than a pseudorandom function or a VRF, which has residual pseudorandomness, because it's not a decisional. It's not saying distinguishes from random. It's much easier. It's just saying all you have to do is come up with one more evaluation. And if you can't do that, then it's unpredictable. So some of the things that let's just think about, like what if it's unpredictable, what properties does this function have? Well, if it's unpredictable, it must be preimage resistant. Otherwise, you could just recover the key from the commitment to the public key. Sorry, you could recover k from the commitment ek. And then you could just get as many evaluations as you like without even using the oracle. It must be collision resistant because a collision would give you, you could evaluate you could query the oracle on the one M, and then the colliding M prime would not be in one of the queries and would have the same output. So a collision in the inner function would give you a collision in the outer function as well. And it must also be non-commutative in this sense, where if you start by walking with M and then by walking with K, then that should be a different output to K and then M. I mean, otherwise you could take the EK that you're given and walk it with M, and then you would be able to come up with one more input output pair. So this kind of looks like the CGL hash function, but it doesn't seem, it's a bit more complicated. So at a high level, what I want to say is basically that maybe good instantiations of CGL are unpredictable. More precisely, I'm interested in that radical isogeny variant, because that's what we want to use to build the protocol. But it's just an interesting open problem that I've been thinking about for my whole PhD, really. And it's very hard to get your hands on the security. So let's first talk about like some obvious things. I mean, E is going to be the set of supersingular curves. Your K is going to be either -1, 1 to the n, so you're doing walks of length n, or 0, 1, depending on how you define the hash function. E0 must be a curve unknown endomorphism ring. Again, I'll come back to that. And then the function is just CGL. And for security, we need n to be bigger than 2 lambda roughly to prevent kind of graph search attacks, like claw finding attacks. And you need log p to be roughly bigger than 2 lambda to avoid Delft Galbraith type attacks to recover the isogeny path. So that's just for the one-way function, essentially just for preimage resistance. But beyond that, it's very challenging to analyze this hardness assumption. Like it seems basically that what makes this secure in some sense is that the directions are kind of algebraically unrelated to the structure of the graph itself, to the structure of the isogenies, because in particular, like the choice that we made with by defining it by residuosity of the square roots, it's kind of, you can't really get your hands on what the residuosity of the square roots would be. At least we couldn't. And even if you could, maybe there's a different choice. Maybe use a PRG or something like that instead. I don't know. There's different options for how you do that. Expanded mixing lemmas don't apply because like in the case of kind of a lot of the protocols that are built up from CGL hash function, you can kind of just get away with, if you walk long enough, you end up anywhere in the graph. But in this setting, we actually have a fixed key K, right? So every evaluation is correlated, so it's not random. So there's no way you can use that to kind of justify the security directly, at least. And so what it looks like is you're getting this kind of commitment walk by K, and you're getting a bunch of these images here. And of course, an adversary can try and come up with whatever message they like to try and get to this kind of middle point here and possibly correlate them. So you could possibly end up with, if you change the least significant bit of the message, you would end up with this middle curve kind of being distance 2 apart, so there'd be 4 isogenous. And so that's maybe one thing we can investigate, right? We can look at, do distinct correlated messages have uncorrelated outputs? So what does the outputs look like when you have correlated messages? And so this is one quick side tangent before we get back into that question. Some trivial things that don't work. So if you walk with the key first, then of course you walk along with your key, and then you choose 2 messages which differ only in the last bit, and then you end up with 2 things that are 4 isogenous. So that doesn't work, but it's fine because we weren't even thinking about that anyway because of the way we defined the the unpredictable function. It's just an observation. And the second thing is, if you know the endomorphism ring, you may be able to find an endomorphism of norm 2 to the 2r for r less than n. And if you have one of those, then you have a cycle in the graph of length 2r, which gives you a collision where both of the paths are length r. Okay, so you take these collisions and then you keep the remaining n minus r bits the same, and you have a collision in the unpredictable function. Now, it's worth pointing out that if you had an efficient algorithm which takes as input a representation for the endomorphism ring and tells you that for sure you don't have any endomorphisms of norm 2 to the 2r in your endomorphism ring, then it would be fine. Well, I think it would be fine. But if you don't have these endomorphisms, then you're okay. So, but it's unclear. It seems like it could be a challenging computational problem, but it would be very interesting because in that setting, if you had such an algorithm, you could actually publish the endomorphism ring as part of the public parameters and say, check this for yourself. This is a good endomorphism ring. And then you don't have to worry about having trusted setup. So it's a very powerful thing, and it's something I'll definitely investigating. Okay, so experiment design. So I wanted to try and look at, do correlated messages, do they lead to close outputs? It was a tricky thing to think about how to design an experiment that would be efficient, like that would actually run on my computer before I finished my PhD. So starting off, I had to use quite small parameters. So I just looked at walks of length 13 and a 13-bit prime, 8191. And what I did was I sampled one uniform key, and then I sampled 1,000 messages. And for each message, I evaluated CGL M then K. And then for each message, I looked at a set of correlated messages M prime, and I just took the same amount of random strings of length 2n. So that's CGL-R, which is essentially a random walk of the same length as M prime then K, or M then K. And I wanted to see, do random walks, do they end up with vertices that are just as close as correlated message, as the images of correlated evaluations? And so what I did was I chose two different ways to define correlated. I'm interested if anyone has any alternative suggestions, but I started off with these. The first is all messages which are Hamming distance 1 from a message. And the second one was I looked at all messages which differ only at the least four significant bits. So that's kind of like maybe a reasonable estimate. You want things that are kind of close in that middle part of this walk, right? Because that's the part that the adversary can kind of control. And then I did a bounded Dijkstra search, so it's only looking at whether or not things are closer than or equal to 8 apart. And then if I found that either a random CGL-R or CGL-M prime then K was close to CGL-MK, then I kept track of that. I stored that. And so these are the two tables that I got, and they look pretty promising. But I need to do some more statistical analysis on this. And yeah, the statistical distance was less than 0.025, but I don't know if that's the right thing to be calculating here. So I need to do more work on that. But yeah, the graphs are at least interesting. Right. So why are we looking at unpredictable functions? Well, the idea is that I'm going to be building a verifiable random function from the unpredictable function, and it's the way, this is a convenient way to do it because it's more reasonable to come up with a hardness assumption about unpredictability than it is to actually have truly random, or at least having outputs that look like random. And so what's a VRF? Briefly go over the VRF. It's a pseudorandom function that has verifiability. So it's a tuple of algorithms: setup, key generation, evaluation, which takes the secret key message and gives you an output, which is kind of the output of the function. a proof pi, and a verification algorithm which takes the public key, the message, the supposed output, and a proof, and accept or reject. So it tells you whether or not this person with the key pair did evaluate this function correctly, and if they did, should be random. And so the motivation for this, I think VRFs came about with kind of leadership election protocols and were popularized for blockchain proof of stake. So the idea is that if you're the leader of a specific block, the state itself is the block is the state itself, and then you kind of choose the next leader for the next block, and you use the state as inputs to the VRF and your key pair to prove that the evaluation was random. And so the applications are in blockchain proof of stake, randomness beacon, so generating kind of verifiable randomness, DNSSec, and maybe like a transparent online casino, so you could have verifiably shuffled cards, perhaps. And having efficient, robust post-quantum VRFs is still largely an open problem. So either they tend to have an ad hoc assumption, as in our case, or they tend to be less efficient. And there's actually two other new isogeny-based protocols in the last couple of years. One of them is Yifu, Lai, Capybara, and Tsubaki, which has a very nice reduction to group action decisional Diffie-Hellman, but it suffers from very slow proofs, like hundreds of seconds, I think. Don't quote me on that. And then LaRue's is based on kind of the new variants of ski sign. And it has a one more isogeny type assumption, which is again very related to what we have. We essentially just have this is a one more assumption as well. So it's a common framework to kind of come up with essentially an unpredictable function. And so the security properties of a VRF, verification. So provability is just basically says that an honest evaluator should always be accepted for all messages, and unique provability. So unique provability basically says that it should not be possible to come up with two different outputs, two distinct outputs that both have accepting proofs. This is challenge. Full unique provability actually says that even for an unbounded adversary. But actually, if you've got a function that's not injective, so if it has collisions, even if it's collision resistant, then it can't be fully unique provable, because the unbounded adversary could just find a collision, and then that would allow them to break this. So so often people relax this to weak unique provability, which is just you just require the adversary to be polynomial time. And the one that we care about for this is residual pseudorandomness. And this is basically, it's related to unpredictable functions, as you might imagine. But the idea of this is that an adversary should not be able to win this game with non-negligible advantage. And so you set up some parameters, you generate a key pair, the adversary is given the public key and an evaluation oracle for the VRF. And then it has to pick one message, which it hasn't queried to the evaluation oracle. And the game then samples a random output, a random string, and the adversary has to distinguish the output from the message they gave, or has to guess whether or not it was the output from the message they gave or was a random string. And so the idea is an adversary cannot distinguish the output of the message, even if they're given access to an evaluation oracle. And the reason why I bring this up is that we showed that you can, in the random oracle model, given an unpredictable function and a non-interactive zero-knowledge proof of knowledge for this relation, which is kind of just showing that your unpredictable function kind of commitment is consistent with the evaluation you gave. If you can prove that that is consistent, then this transformation on the right allows you to have a verifiable random function. And as concurrent work, which by Junta and Stewart, which was a little bit before us, they proved the security of an equivalent construction, which technically they define verifiable unpredictable functions rather than having an unpredictable function and an associated proof. But the transformation is equivalent. So and they also showed that their transformation shows. Sorry, they also showed that their transformation satisfies unbiasability, which is a property that was actually needed from VRFs to guarantee fairness in proof of stake applications. So it was kind of a property that was deficient from the original properties of VRFs, and they show that this transformation provides fairness. Sorry, provides unbiasability, and that's the name of the paper: unbiasable verifiable random functions. And I won't go into the details of the transformation. It's just good to know. And that's the end of part one. So now I'm going to kind of go through some and hopefully inspire you to use generic proof systems for your applications. So in the context of isogenies, suppose we want to prove kind of the most general isogeny relation, which is kind of just proving knowledge of a cyclic isogeny, a power smooth cyclic isogeny. And now, like in most, obviously this is changing now that we've got so much, it doesn't apply to KLPT or Carney gadget type protocols. But if you've got a power smooth isogeny, you probably care about this relation. And prior approaches were based on sigma protocols, and it would be loosely based on an SIDH squared. So you'd have this, you'd be trying to prove knowledge of this isogeny, and you commit to all of these arrows here. You'd sample a random phi prime and generate these two isogenies here. And you would either open this one, or you'd open this one or this one. And this has various challenges. I mean, firstly, it has small challenge spaces, so you have to do a lot of repetition. So it becomes computationally expensive, and the proof size grows. You also need rational co-prime torsion. So these isogenies psi, you need to have rational En torsion. We'll just call this degree n. So you have to work over field extension, or you have to have a larger prime. Okay. And they require additional assumption, except for the supersingular curves you can trust, because they walk far enough that it's statistically indistinguishable from random. But then it becomes computationally expensive because you have to do really long walks. And also, one minor annoyance is that the extractor in the special soundness proof only doesn't recover an L to the K isogeny. It recovers an n squared L to the K isogeny. So it's technically not exactly a proof for this relation. It's kind of a slightly different relation. Although it's not clear whether or not that actually matters. No one's ever found an issue with that, but it's just another kind of annoying thing. So can we do better? So like, I guess we want to try and use generic proof systems maybe. So I'm calling them generic proof systems, but I know that cryptocurrency people love to call them zk-SNARKs. A zk-SNARK to me is just a non-interactive zero-knowledge proof of knowledge that's also succinct. In other words, the proof scales polylogarithmically in the size of the witness. Technically, it's an argument, not a proof, which means that the soundness doesn't hold. The soundness only holds for computationally bounded adversaries again. But in the world where we rely on computational problems, which we live in isogenies, this doesn't really matter. And they are called general because they prove kind of very general expressions, general relations, like R1CS or AIR, which is algebraic intermediate representation, and polynomial systems. And these all just work over a fixed finite field that's a parameter as input. Prior approaches required FFT-friendly fields, so you needed if you have these parameters as part of your instance, which will be the number of constraints and the number of variables, and you need that roughly that 2 to the log of the number of constraints or variables needs to divide the multiplicative group of the field. So in the isogeny setting, this is like less than 15. So you need 2 to the 15 to divide the multiplicative group of F. And this doesn't work if you're working over FP for 3 mod 4 because you've got 2 times an odd thing. So you only have what I'm saying is that the highest power of 2 that divides the multiplicative group over FP for 3 mod 4 is 2, not 4. But conveniently, FP squared has a very, very, very big power of 2 divisor because generally speaking, we want P to be power of 2 times something minus 1. So FP squared works fine. But in some settings, we might actually want to work over FP. And conveniently, new approaches are using expander codes, and which use expander codes are field agnostic. So they don't really have any requirements on the field. And these are used in the context of ECDSA signature verification, where you're working over a field that doesn't satisfy these conditions. And so the alternative was to literally take the arithmetic that encodes ECDSA verification and put it into a different field, which is not very efficient. So this is kind of a solution proposed for that. But it conveniently also helped us. So rank 1 constraint systems are parameterized by a finite field, a number of constraints, and number of variables. And your instance consists of 3 matrices, which are m by n plus 1, vector v, which is kind of your public input variables, your q, which is your modulus, and w, which is your secret input variables, and your intermediate variables in the computation, because you obviously don't want to leak those to a verifier, because that could leak the secret input. And then what you're saying is that a times z is kind of 1 plus your public input and your secret input. We need this 1 here so that we can encode constants in our equations. And so you have az, which gives you a vector, a length m vector, bz and cz, and each row of this kind of equation here, where the circ is Hadamard product, so it's just coordinate-wise product of vectors. Each row of this equation here is basically encoding a linear expression in z times a linear expression in z equals a linear expression in z. So it's very simple. It's basically just encoding quadratic systems in a nice matrix. And so I guess the point of the rest of this talk is to try and show you how you can tweak things to make them into quadratic systems in isogenies. So the first one we did with Qilong Kong and Yifu Lai we represented an L to the K isogeny from E0 to, we'll call it E to EK, not E1, by a sequence of J invariants. So basically just a walk in the graph. So we'll encode it as a sequence of J invariants, and then if a cyclic isogeny must satisfy these equations. So we're using the modular polynomial this time. And so at the public starting curve, the J invariant of E0 must be adjacent to J1, and then each intermediate J invariant must be adjacent, and then the last secret J invariant must be adjacent to the public endpoint of the walk. You're trying to prove that you know an isogeny from here to here, and you know the intermediate sequence by the system of equations. Sorry. I'm just looking after a dog. Luna, come on. Okay. So we've got the modular polynomial can be represented as this. We rearrange it into this. It's got a lot of personality. Okay, so the reason why we've arranged it in this way is to try and get kind of minimize the number of quadratic equations. So just as an example, if we take a walk of length 1, in this equation here, we need to compute the squarings of each J invariant and the cubings of each J invariant, as well as the product of each successive J invariance. So for walks of length 1, we have input J0, J1, the squares and the cubes, and the products. And so the first row of these matrices is just basically saying that J0 times J0 equals J0 squared. Because the verifier doesn't actually know what the prover is inputting into this. So he needs to be convinced of everything, right? The next part is saying that J1 times J1 equals J squared, and then J0 times J1, sorry, J0 times J0 is J cubed, so we're checking the cubings, and so on. And then the second last one is taking J0 times J1 equals J0, J1. And then the last row is basically this equation here, because we've pre-computed all the squarings and cubings. And so you can now extend this so that for paths of length k, you get 4k plus 3 variables and 4k minus 2 constraints. And there's one thing missing here. This will be satisfied if the isogeny is cyclic, but if you backtrack in this walk, you would get a non-cyclic isogeny, but it would still satisfy these equations. So there's one solution to that. You can simply check that every second J invariant is distinct. And you can do this efficiently. It only adds an extra k variables and constraints roughly. So it goes to about 5k. But technically, it doesn't allow you to prove kind of if you've got a double edge and you walked back along that double edge, it wouldn't allow you to prove that. So it would cover almost all cyclic isogenies, and it would exclude non-cyclic isogenies. But we don't care about this because the next solution is even better. So now we can use radical isogeny formula to prove a cyclic isogeny in half the number of constraints. So we represent the 2 to the k isogeny by sequence of curve coefficients, AICI, such that each successive coefficient satisfies these formulas. And then we can rearrange these to make them look like nice quadratic equations so that we can put them into an R1CS. So it's worth noting we don't care about directions here. This is we're not proving anything about directions. We're just proving that we know a path, right? So it doesn't matter what routes you choose here. So you get these two equations, and they already are quadratic. So we can put them directly into the R1CS instance here. And so if we've got a walk of length 1, we've got our curve coefficients and 1. And if you just were looking at this while I was talking, you might see that it matches these two equations here. So you've got 4 times A0, 4 times A0, times negative A0 plus A1. That's this part of this equation. And then on the right-hand side, you've got 6C1 minus 48C0. And you get the idea, hopefully. And now the next thing is, how can we actually prove knowledge of these CGL inputs? So to be clear, we want to prove this relation, right? We're given a curve, the endpoint of the walk, and the witness is a message such that I can evaluate CGL from a 0 with the message and get to EN. So now I already want to have a way to express these roots using a system of equations in a way that minimizes the degree. Okay, so for now, I want you not to think about the code in the red blocks. Just treat it like it's not there. Okay, so if the real value of alpha I is not a square, then we just negate it. So it doesn't matter what square root you start with for CI at each step. We'll just make sure it's always the one such that the real value is a square. And so then we get this system of equations, which is, I've just taken this one here and substituted it into here to remove this cubic term, which is annoying, and you don't need it because you already have, it's already determined by this equation here. So we've managed to reduce this equation down to one quadratic equation rather than a cubic. We now also have this equation here, which is kind of ambiguous. What does the real value of alpha I mean as an expression, as a polynomial? And we also have this here, which is defining an alpha I. And this kind of fixes the direction, I guess, kind of fixes the choice of alpha I. Lastly, we have this equation here, which basically just guarantees that your message is actually either -1 or 1, right? You don't want to be putting in messages which are not valid messages. Because you would just get you might just fly off into a curve that's not even super singular. So we definitely need that. So how do we realize this real function? Well, you could use this. You take, the Frobenius fixes the real values. So if you add x and it's Frobenius, it'll negate the imaginary component, so it'll cancel out, and you'll get double the real value. And then you just divide by 2. But this requires log p constraints, because if you exponentiate by something, you're going to have to do essentially square multiply. Well, not quite square multiply, but you'll have to do a kind of squaring ladder, which is going to give you log p constraints, and that's at each step, that's too costly. So the solution is we just work over FP. So we actually embed the arithmetic into FP. And so just a quick explanation of how this is done. So addition is straightforward because, well, I mean, there's no cross terms or anything. The real values, I mean, it's just like a vector space. And squaring is okay. Well, I guess I'll start with the arbitrary R1CS constraints. But one thing that's important to note is that the real and imaginary functions are FP linear. So I can always take linear combinations of things, and I'll be able to pull them through with the function. So that's kind of the trick that's happening here. I'm not going to go into too much detail, but the point is that I'm essentially just using the formulas for FP squared arithmetic, and then relying on the fact that another key thing is that my coefficients, this only works if my coefficients C, L, D, R, and EO, all these coefficients here are all only in FP and not in FP squared. So then what I do is I basically pull these out of the function, and I essentially just have FP squared multiplication law. And that gives me three constraints over FP. So if I have one constraint in FP squared, which is arbitrary, then that gives me 3 constraints in FP plus an additional variable. Now we can do better with squaring. And with squaring, we get only 2 constraints and no additional variables. So what that means is that if I have V variables, S squaring constraints, and G general constraints, I get 2V plus G variables and 2S plus 3G constraints of FP. So I can encode this FP squared system of equations in FP and then convert it into an R1CS instance in FP and do it all in FP, and that's equivalent. And so now another thing worth pointing out is some of these values were already in FP to begin with. So this beta I is in FP. The real value is in FP. So this is actually just an FP constraint. Same for this constraint with the messages to guarantee that they were -1 and 1. This is an FP constraint. This constraint here, I've got an FP element with a FP squared element, so I can actually do a little bit better than 3 constraints here. I can do it in 2. So that's why I get 9n plus 4 variables and 9n constraints. So this gives me, that's because I can do it with 2 here, 3, 1, 2, 2, 1, and that gives me 9. Okay, so now I'll talk about what's going on here. So turns out that you do fall into the situation where your real values are 0, because it may not even be a concern because it happens with negligible probability. But it turns out if you start on an FP rational curve, then you're kind of guaranteed almost always to hit, or at least I guess 50% of the time, to hit this scenario where you have 0 real value and then imaginary value in alpha I. And that's because if CI is in FP, you take the square root of Ci, either it's a quadratic residue in FP and you get an element of FP, or it's a non-quadratic residue, in which case you get something which is 0 plus something times I. So you actually hit this a lot. Now, I stress it's not really a concern because we want to use a curve of trust of unknown endomorphism ring. And so you kind of want to be somewhere far from the FP subgraph anyway. So it's probably going to happen with negligible probability. But if you do care about this, then you can turn this, and it's also not a function technically anymore because now you have essentially two possible outputs. So if you want to fix that, you just simply have to add a set of conditional constraints. So you kind of have essentially branching going on. But it's still, now it's a function, and we go from 9n plus 4 variables to 13n plus 4 variables and 14n constraints. So it's not a huge amount of overhead. And it turns out that actually it doesn't affect the performance because you're essentially interested in what power of 2 bounds from above the number of constraints and variables. And in this case, if n is 2 lambda, so if it's 256, for example, then both of these things are greater than 2 to the 12 and less than 2 to the 13. So our performance estimates are the same. So it's fine to add this. I won't go into the details of what those constraints are. But so here's just a kind of very rough performance estimate, because one of the issues with these generic proof systems is that we don't have flexible implementations that support arbitrary fields and support arbitrary R1CS instances in a way that's very easy to implement. It's all very like hard coded. But randomized instances, you wouldn't behave them to expect very differently. Yeah, so I guess this was the cyclic isogeny relation, and this is kind of what we could expect from performance. This is I mean, these are orders of magnitude, I guess. And CGL, this is the CGL relation. And this is I didn't describe what this was, but this is essentially when you take the CGL evaluation of the message and the CGL evaluation from the message curve to the endpoint of the evaluation, and the CGL evaluation from the E0 to EK, which is kind of your public key, right? So this is just basically the proof that ensures that your VRF was honestly computed. And it's essentially two compositions of this with the message input the same. And yeah, so that's kind of the very fast proof and verification times, which is quite cool for an isogeny proof. I guess that's what makes it interesting to me. Yeah. So that's everything, I think. I guess there's some things here, but we don't have to talk about it because I'm over time.
Thank you very much, Shai, for a great talk. As always, feel free to unmute yourselves or just type a question in the chat if you have anything. Maybe I can start with a question. So I'm just wondering, do you know if there are like other post-quantum VRFs not from Isogenies, and if so, how they compare to these Isogeny-based ones, or are there none?
Yeah, so just trying to remember, there's actually not that many other ones. It's not fresh on the top of my mind, but I believe there's a lattice one, but it has slightly questionable security, I think. But I don't think it performed. I think the best performer for sure is in some metrics we perform slightly better, but the LaRue's VRF is overall performs very well as well.
Okay, thanks.
I also have a question. Thanks for the talk, by the way, and for doing it upside down. I guess it must be difficult for you. So if you do this for a larger L, do you know how the radical isogenies scale compared to modular polynomials?
I think they scale favorably. I think it's something like I may be wrong. It may be something like L minus 1. Essentially, the polynomials will be degree L minus 1. So, sorry, degree L, right? Because you're computing Lth roots. So essentially, yeah, you're going to get degree L polynomials.
Yeah, so I guess it's L compared to L squared then.
Yeah.
Okay.
Yeah.
Okay, thanks.
I also had a question about the proof systems. So what you presented was like power of L proofs, like for isogenies of power of L for some prime.
Yeah.
So what if you had some sort of B smooth isogeny, like a B-side type isogeny? How would the generic proofs work? Or like, would it be easy to extend, and how to extend the situation?
Good question. Yeah, I think it should be doable. I guess you have to make a choice of which ones you want and what order you want to do it in, but it doesn't really matter, right? So you can express, I mean, it's just the R1CS will be messy, right? Because you have to like, it's just going to be you're going to have a lot of pages of equations, but I don't see the limitation.
I guess it would perform as worse, like as bad as like the biggest factor. I guess that's what, like in the sense that like the bottom
Asymptotically, yeah.
proving the big factor, and then the rest would sort of be negligible.
Yeah, I mean, you'd still be dealing with like the sum of the degrees, right? But it's like, but yeah, it would be asymptotically, I suppose, yeah.
Okay. And do you think it would still outperform like other isogeny proofs? Like, would the generic proof system for this still outperform like the more tailored proofs, I guess?
What proofs do you have in mind specifically?
I don't know, like say if you generalize the super singular curves, you can trust proof to
Yeah. I think there's definitely, yeah, it would definitely, I think it would definitely, I mean, don't take my word for it, but I would suspect it would outperform that because these already outperform that with power smooth. But and also the benefit of using SNARKs. We're not even really exploiting one of the big benefits, which is that it will scale it should scale polylogarithmically in the size of the witness. So if you're dealing with larger basically the bigger your expressions get, the more you're hitting that curve of polylog. So it's kind of maybe in some sense it would be even faster. I don't know.
Okay, cool. Are there any other questions? Okay, well, if not, let's thank Shai again. Thank you for the great talk and for doing it at an unusual time. Yeah, so that's it for this season of the Isogeny Club. Hopefully we'll see a lot of you at Eurocrypt or at the affiliate days before Eurocrypt for the brainstorm days. Don't forget to submit your ideas for brainstorm topics. We're still accepting submissions, so we're looking forward to hearing your ideas. And yeah, thank you again. And we'll keep the room open for a little bit if people have other questions. But yeah, thank you.
Awesome. Thank you, Maria. It's nice.